Hi, my name is Ariana Bruno, and I'm a mechanical engineering student at the University of Michigan. As a 2014 participant of the Summer Undergraduate Research Experience here at Michigan, I had the opportunity to work in the Department of Biomedical Engineering with Professor Beata Chateau. In her lab, I was able to design and develop a 3-axis positioning system for localized drug delivery experiments utilizing acoustically stimulated microbubbles. Professor Chertouk's current research works with developing microbubble materials for localized drug delivery. The microbubble materials have unique properties to allow for acoustic stimulation by ultrasound. When a drug-containing microbubble is acoustically stimulated by a focused ultrasound beam generated from an ultrasound transducer, the results are the destruction of the microbubble and the release of the drug within it. In order to achieve drug release at specific locations, it is important to be able to accurately control the positioning of the ultrasound beam from a transducer within the environment. In past experiments, the setup consisted of a water tank, a sample holder with microbubble solution, a transducer, and clamps. The sample holder would be submerged underwater and positioned with a simple assembly of rods and clamps. Professor Chertouk would then hold this transducer just above the water so that only the face was submerged. The alignment of the ultrasound beam with respect to the sample holder was done manually and consequently was not precise. My project was to design and develop a system which would accurately position the ultrasound transducer with respect to the sample holder in 3 dimensions.
I began my project by following the typical design process, working from coarse details to the fine ones. I made sure that the requirements were specified, looked into existing solutions, generated design concepts, selected the best fitting concept, detailed the design, modeled and analyzed it, built and tested the prototype, and then finalized it. Although this process is straightforward, I still had to do some problem solving along the way.
I gathered as much information about the test setup from Professor Chertouk and journal articles to define the constraints. I discussed many approaches with my professor to see what worked best for her experiments. The concepts converged to use 3 actuators moving above a tank for 3-dimensional motion. The acoustic instruments would be controlled using the positioning system. The sample holder would be independent with its location being adjustable within the tank. The actuators would be purchased to ensure the most accurate and precise motion. I looked into multiple types of actuators, including belt-driven, leaf screw, ball screw, pneumatics, and even hydraulics. I figured out the advantages of each motion and received numerous quotes to gauge where each actuator was in terms of our budget. Finally, we chose Velmex's X-Slide, a motor-driven lead screw actuator based on cost, precision, speed, and additional accessory items. I focused on the design of the structure for these actuators. During the beginning of the design selection, many of the details for the full system were hard to explain and imagine even with quick sketches. To help select the right concept, I was able to create multiple CAD designs for my professor and I to visually refer to when discussing specific details. This gave us better clarity for selecting which design concept was best for the lab. While generating different designs, one of the problems we ran into were the force capacities of the actuators. We could have went with a larger actuator that was more robust and could hold higher forces, but with that came higher prices, more space taken up on the workbench, and made the accessibility of the tank then much more difficult. One of the initial configurations the company suggested prevented us from using the small actuators because the resulting forces would exceed their force capacity. One of the problems with this configuration was due to using one of the horizontal actuators cantilevered from the other horizontal actuator. With nothing supporting it on the other side, there's too large of a moment force induced on the other actuator, and the side would be unable to move. Additionally, I wanted more traveling distance for the setup. However, this would require either larger actuators that held heavier forces or longer, small actuators, which would both result in much higher cost. Alternatively, I developed a structure that uses a carriage construction that manually slides along the frame and supports the 2 horizontal actuators. The carriage adds additional travel distance and helps to balance the forces in the system. I was able to work with one of the engineers at the company to figure out a new configuration with the actuators. The horizontal actuator would no longer be cantilevered, and instead the structure I would build would support it at the other end to balance the forces better. The horizontal actuator would then be flipped on their sides to allow the vertical actuator to be positioned below the structure and hovered above the tank. This reduced the resulting forces on the actuators and allowed us to use the small actuators. Another problem that arose was due to the strict dimension limitations of the workbench and traveling lengths of the vertical actuator. There is a sensitive focal length needed between the transducer and the hydrophone in order to function properly. To help ensure our design fit our workbench and had no interferences with any of the existing features, I made a full model of the workbench. From this, we saw that the vertical actuator would interfere with the top shelf. We could not compromise the length of the vertical actuator or the height that it would be held at. Eventually, this led to the solution of adding another actuator that would hold the vertical actuator at adjustable height locations, so that when it was under the shelf, it was low enough that there was no interference, and when it was out from under the shelf, it could be located an additional 8 inches above the tank. Finally, it came time to build the structure. I spent many days in the medical school machine shop creating the components for the structure and the carriage. Once the pieces were finished, I assembled all the components and configured the actuators into proper orientation. The detailed CAD model helped to ensure all the pieces fit together as they were supposed to, and there is minimal troubleshooting. During this time, I was also working on the LabVIEW user interface for controlling the system. First, I had to learn the code language of the Velmix controller. I had to then troubleshoot the Velmix LabVIEW driver to work on the system's PC. This driver allowed me to send code from a LabVIEW interface to the Velmix code terminal. One problem with the Velmix LabVIEW driver was that it still required the user to know the terminal code language and input a code into the LabVIEW window. I was able to manipulate this driver to eventually create manual positioning using sliding knob inputs and eliminate the need for the user to write terminal code. The user could input the desired location of a specific actuator in the system, and the LabVIEW VI would convert this information into a code to move it to that designated location. Another problem I was able to solve with the LabVIEW code was the inability to kill the motion of the actuator in a convenient way. Initially, the only way it could be killed was by opening the terminal window and sending the letter key manually. I solved this by having a dialog box open up whenever the motors were in motion to give the user an option to kill the motion instantly. I was able to create VIs that would allow reinitializing the zero position of the actuators, bring the actuators to optimal location for loading the equipment, finding the sample holder in the tank by knowing the location of the carriage, the tank, and the sample holder, and also moving instruments in repeatable incremental motions over the area of the sample holder, which is key in the stimulation of the microbubbles during the experiments. So I'd really like to thank Mike Umbriak for all his guidance and feedback on the design of components for my structure. I'd like to thank Oliver Kripkins over at the Medical School Machine Shop for helping me with some of the more challenging machining tasks of my structure. Zenzu's Lab for all their advice on how they've been able to create their positioning systems for acoustic experiments. And of course, I'd like to thank Beata Chatok for being an amazing advisor throughout this entire project and really giving me wonderful feedback and guidance throughout the entire process. If you have any further questions or would like to get involved, please contact Professor Chatok.